So screen आपको नजर आ रही है?
Yes, sir.
Okay. Let's begin with the next example in pipeline. So this is another application of the Rayleigh's method. And if you have wondered about a suspension system, so this question is about the suspension of one front wheel of a car. So this wheel, and so you have these dimensions are given. L1 is 0.4 meter, L2 is 0.6 meter, L1 and L2. The coil spring is of stiffness, so ये जो spring यहाँ पे given है, इसकी stiffness given है इधर, ठीक है? And the car weight associated with that wheel is 3500 newtons. Okay. So determine the suspension's natural frequency for the vertical motion. Because we are only interested in natural frequency, we don't need to write down the equations of motion. We will use energy method combined with Rayleigh's method. So one thing which we need to consider here is that this suspension system works by the principle that when any bump or pothole, for example, this is a bump and this is a pothole on the road, is experienced by this wheel, so this will get disturbed only once, but after that all the vibration will be dealt with by the spring part. Okay, so this will be stationary and this part will be going up and down. So if you think of this as the pivot point, yeah, and this is your rigid body and this is going up and down. So if we introduce, let's say we track this point and the vertical displacement of this point, let's call that y, and the vertical displacement of this point, because we want to follow what the spring does as well, let's say that that is x. Okay, so we can now think about, and this point is fixed, so we can now think about a similar triangle, okay, where this point is fixed and this point has a displacement of y, and this point in the middle, I don't think it's in the middle, but actually it's L1 and L2. This is x, yeah, x is the displacement of the spring, and from here to here it's L1, and from the total length is L2. And if we want to connect x and y, we have to think about this common angle. If you call this theta, then the tangent of theta, you know, is on one hand it's y over L2, yeah, y over L2, but on the other hand it's x over this distance, which is L2 minus L1. Okay, in the book this is a typing mistake, and there in the denominator you will see x divided by L1, which is wrong. Okay, because in a similar triangle you have to find a common point. So this will remind us, we can now ignore sine tangent theta, because our purpose is now, this was our purpose. So whenever we want to relate y and x, we will use that relationship. So coming back to this problem, for the natural frequency, we know that we have to use the Rayleigh's method, and for that we need the expressions for potential energy and for kinetic energy. So what's the potential energy? One more thing is that the displacement of the mass, actually this will be the displacement of the mass. Okay, and the spring is here, the spring is fixed here, and this is actually an effective mass. So the mass of the wheel and the mass of the vehicle, and I mean all the effective mass relevant for this vibration will be lumped here. So and we also need a reference. Let's say this is our reference. The reference means that when at this point we at y is equal to 0, we can take our potential energy from the gravitational potential energy to be zero there as well. So which means that if it comes down, the potential energy will be minus mg y. Okay. Now what is m? Yeah. So instead of writing m here, because then we have to multiply g here, a good idea is to replace this mg with the weight w. Why? Why this is a good idea for this particular problem? Normally we are happy to write mg because now we expect m to be given. In this case we are given the weight, okay, 3,500. So that will be directly substituted here for w. So I'm just writing wy. And for the spring you will have half k, the value of k is also given, kx squared. And because you have the effect of gravity, so you have to include the static deflection as well. So x plus delta st, static deflection, and you also know, okay, that is our expression for the potential energy, minus w y. And if we expand this, you will have half k x squared plus half k delta st squared, and you know the other term, twice half cancels, k delta st will cancel out with wy, because we know that w must equal k delta st. So as we have seen over and over, this will get cancelled out. So that is the expression for v. And now we need an expression for k, the kinetic energy. So kinetic energy, that will be half m y dot squared. Okay. So now you see the expressions of v. The expression for v involves x and the expression for k involves y. So that's why it's important to use this relationship. I can now, what I can do here is that I can rewrite the expression of v, yeah, by replacing it with k, and I can replace x with L2 minus L1 divided by L2 times y. Okay, so L2 minus L1 divided by L2 times y, and I square both of them, and it's half delta st squared. I think it's, there's a k as well. Okay, half k will be there. So now I have expressions for k and v. Okay. Okay. So now, and this m is now a question, because m, we don't have m, we have w. Okay, w is the weight. So instead of writing m, I can write w by g. Yeah, I hope you get this point. Yeah, half w by g, because w by g will give me mass. So now you know that in Rayleigh's method I will need k max, and that should equal v max minus v min. Okay, so what is k max? K max is half w over g y dot max squared. Okay, and v max is half k L2 minus L1 L2 squared y max squared, and plus half k delta st squared. And what is w min? W min is this minimum value is when y is 0. So if I set y to 0, then v min is simply this thing. Okay, so it's minus that same thing, and which means that I can now cancel these two. Okay, so I can now just remove, because that static deflection is plus in v max and it is minus in the second term. So now it boils down to this last equation. In this last equation, on one side we have y max, on the other side we have y max dot. But we also know that because this question is about natural frequency, and natural frequency is a question that is asked only when you have simple harmonic motion. We do have simple harmonic motion here because we only have mass and spring, and we ignore friction, we ignore any losses. So for simple harmonic motion, you know that the maximum velocity and the maximum displacements, they are always related by omega n. We have seen this over and over. So I can now replace this y dot maximum by omega n. Don't confuse it with this w. Omega n times y max, and I then take the square on both sides. So now I can get rid of y max squared, and this equation can be solved for omega n, and you're done. Okay. Is there any question about this example? Okay. Now the problem we have after this is very much like this. Okay. The only difference is that instead of this complicated, we needed this L2 minus L1 because the pivot was here and the label was here. If this was our label, then it would have been easier. Okay. Maybe that's the reason this mistake is can be found in the book, because maybe somebody did not notice this. But in the problem 4.35, the labeling is done correctly. This is your pivot point. You label this as L1 instead of labeling this as L1, and the overall length is L2, and again you have mass in the middle, or not in the middle but somewhere in between, and x is the displacement of k. So if I label the displacement of mass as y, I can again connect using these two, connect these two using the similar triangle concept. The common angle will be here. No, actually, no, I should follow the pivot. Okay, this is the pivot. This is the pivot. So if this is x and this is y, this is the common angle theta. Now this time we don't have these lengths, okay? So we can now follow these lengths. The length from here to here is L1, and the length from here to here is L2. And I know that x over L2 and y over L1, they both give me sine of theta. And I can now ignore sine of theta, and I can connect x and y using this relationship if I want to. I'll keep that in mind, and I start. And another thing is that the equilibrium position corresponds to x is equal to 0, which means that the gravitational potential energy is 0 there at x is equal to 0. So if we, because this motion y and x, they are both downward in the convention, our conventional term for potential energy will be minus g. So I will start with potential energy, which is half k x plus the static deflection squared minus because reference is 0 for us. Okay, so you are going down by convention, mg y. Remember, it's not xy because mass has displacement y. Now in this expression, we would like to get rid of okay, let's see. I mean, first let's simplify this. So this will be half k x squared plus half k delta st squared, and the other term twice half cancelled, k delta st will cancel out with mgy because mg is k delta x, k delta st. So you have only this term left, and kmax, sorry, not kmax but k is half m y dot squared. Okay, y dot squared. So this means that we should replace x with y because we want to have y. So x will be, from this relationship, x will be L2 over L1 times y. So that means that our expression for v will be half k L2 over L1 y, and I square both of them, and half k delta s t squared. So now I have expression for all. I can now get rid of this because this served its purpose. And one more thing is that, okay, so we can now simply write Kmax equals Vmax minus Vmin. So let's plug the values. Kmax is half my dot max squared. Vmax and Vmin, remember, in both of them, this constant will be there. Okay, so this constant will be part of Vmax as well as Vmin because this doesn't change, so it will cancel out. So it's only a max of this and a min of this. Min is 0 because y is 0 is the minimum value, so we only write the maximum, half k L2 over L1 squared y max squared. And because this the motion must be simple harmonic, otherwise you wouldn't be asking for this question, natural frequency. So for simple harmonic motion, we know that the maximum velocity is omega n times the maximum displacement. So I just replace that as well. So it will be omega max squared times omega n squared. So I can now cancel out omega max squared, and I just solve this for omega n. So you see, this question was very similar to this question. Okay. If you, one thing is important, that in both these questions, the mass, the rigid body, and the spring, although they are not on top of each other like that, but they are connected by rigid body, rigid links. So it's more visible here. This rigid link, which is massless, but it is connecting M and K, which means that M and K, the gravity, the gravitational force mg, which we call W here, will have an impact on K, and that's why we have to include this static deflection. Okay, so you cannot say that okay, this M is here. If we remove this connection, and if M and spring, if they move separately, independently, without a connection, then we will have to ignore this term. Yeah, because that deflection cannot be there. But now we know that any motion of M will have an impact on K in both these examples. So they don't have to be on top of each other. The gravity can affect mass spring through any rigid link. So this is also the other problem, which requires Rayleigh's method. It explicitly says that. So if we now look for this is important, small angles of oscillation. Small angles of oscillation mean that although this rotation will mean that you have a motion in circle, but small angle of oscillation means that because this is the pivot, so the motion of the mass will be nearly horizontal, okay, and the motion of the spring will also be nearly horizontal. Yeah, the rotation part can be ignored. Now if this is the pivot, we can connect the tangential displacement of M and tangential displacement of these springs, okay, because this is the pivot. So as this mass moves here, this mass will move here, okay. So what do you think will be the tangential, if this is theta, what will be the tangential displacement of the mass? You know, from the pivot, this distance is L, so this will behave like a radius in a circle. So this displacement will be L2 times theta, okay. So if the velocity is theta dot, this displacement will be L2 theta dot. Okay, we need that. Why do we need that? We need it for kinetic energy, okay. So if I want to write the expression for the kinetic energy, it will be half m v squared, and that v is maybe we can do something else. We can do something else. How about using half I omega squared? Half I omega squared. No, but we don't need that, okay? If we can figure out the tangential, this is a point particle, this is massless, so we can use tangential velocity. Okay, tangential velocity is L2 times theta dot. This is like V and squared. Now from this pivot, this horizontal displacement will be L1 times theta dot. Okay, because here the radius of curvature is L1. Now this L1 theta dot, and here we don't need dot. Here we only need displacement because spring energy depends on displacement. Now this spring will be compressed, and this spring, as a result of this motion, will be expanded. Now, as far as the energy is concerned, it doesn't matter. Yeah, whether you compress a spring or whether you expand a spring, the energy will still be half k and deflection squared. And because there is no effect of gravity here, so we'll simply say half k L1 theta squared. Okay, and because both springs will have the same term regardless of minus and plus, because square will make them minus, so it's actually effectively 2k. Yeah, because there are two springs. Now this is the beauty of energy methods, because normally when you're not using energy methods, you will have to say, oh, whether the force is minus or plus, action, reaction, all these symbols. And energy, you don't care. Yeah, you don't care whether they are in series or whether they are in parallel. You still write the overall energy. Now the gravitational potential energy, there are two ways. If you take this as your reference, then this mass is above the reference, so you will have plus mgl2. Yeah, but we can eliminate that if we change the reference. I will choose this as my reference. So I will say that the gravitational potential energy will be 0 here, and that means that I don't need to add anything because the mass stays there. Yeah, its small angle mean that it will remain horizontal, and k do not contribute to gravitational potential energy, so these are the only two terms. So now I need to write the maximum and minimum values. What is kmax? Kmax is half m L2 squared theta dot max squared, and Vmax is k because 2 cancels out, L1 squared theta squared max, and Vmin is 0. Yeah, because when theta is 0, you get the minimum potential energy. So you just say, okay, now you apply the Rayleigh's method, so Vmax minus Vmin, and that means it's half m L2 squared theta max dot squared equals k L1 squared theta max squared. And for simple harmonic motion, you can again note that theta max dot will be equal to omega n theta max. So I can now replace this dot squared by theta max squared times omega n squared. Cancel out this and you solve this equation for omega n. Okay. Is there any question? Actually, here when we were relating these two, L2 theta dot, this is also a consequence of similar triangles. Okay, you can also you have this pivot and you can have these similar triangles here. Okay, okay. No, wait a minute, let me just revise the similar triangle stuff, because I'm just suspecting that maybe we need to revise that. If I have this triangle here, okay, so if this goes like that, if I call this as x, which is or maybe I call that y. Okay, so y is L2 theta, and this is the pivot. And if I, yeah, if this is now if I call this as x. So this is L2, this is L1, this is the common angle, so it will be y over L2 will be x over L1, okay? And I assume x to be positive, okay? So x will be equal to L1 over L2 y, okay? So this means that this will not be L1 theta, okay? This was wrong. This will be L1 over L2 y, and y is L2 theta. So y is L2 theta. So it is L1 theta. Ultimately, you get the same thing. So although I did not have any justification for that, but now it turns out that it gave me exact results. I was actually using my common sense of radius of curvature. So this will give you L1 theta. Yeah, but you can make that rigorous by using following this reasoning. So if x is equal to L1 over L2 y you know is L2 theta, and this L2 cancels out, and you get x is equal to L1 theta. Now this example actually introduces a new topic, uh, and before that, let me just show you one table, and you will see why this topic is important. If you can remember this table, we had this table for springs, okay? We had this table for coil spring, and then a solid rod and simply supported beam, and for all of them we wanted to have an entry for the spring constant. Now why was this needed? Because we had real geometries and materials, so there were actually physical, or you can say real springs, and the constant we have is for ideal spring, okay, for ideal spring. So it means that in these tables we ignored something, and that was the mass. Okay, we did not consider it, but it doesn't mean that it will not have a mass. It will have a mass. Similarly, in this table, you have torsional springs. Yeah, so you have torsional spring property of this configuration and this configuration, but because these are real springs, they will have inertia, rotational inertia I. So there is a need when you actually have a model, physical model. I mean, I wouldn't say physical model. Even if you have a mathematical model, you need to have both this property and that property. So this example will now introduce you to that concept. That if we have a physical situation which has, let's say, this concentrated mass, so concentrated mass can be modeled as a point particle, तो उसकी तो कोई spring property नहीं होगी. लेकिन जो ये mass है distributed rod का, इस rod की दोनों properties होंगी. इसकी spring property भी होगी. So you model that as a spring using that table which I just showed you. Yeah, and this, because this will have mass as well, so you have to represent this by a point mass. Yeah, and that point mass, so let's say I replace this by a point mass, and I replace this by this is already a point mass, and then I combine these two, so I will have an effective mass at the end. Okay, so your job in this example is to determine the equivalent mass of the rod only, not of this MC, but of the rod. Actually, the rod shown acts like a spring. Yeah, this rod. Okay. So this mass is added at the end. We first need to convert this to a point mass, And when in this diagram, we will combine the effect of the rod and the concentrated mass. Okay, that's the idea. So if I now take any small element in this rod, that element, if the mass of the rod is mr, let's say the total mass is mr. Okay, so the this small element will have a mass dmr. Let me just write dmr. So now I have a small mass dmr. D is for differential, and its height is dy, and let's say the area of cross section is a. Okay, cross section is a. So dm is the mass of this element. Now what will be half times this mass times, if the distance from this pivot or the support to this point where we are making this calculation, if this distance is y, okay, if this distance is y, so y dot will be the velocity. Okay, y dot will be the velocity, and the square of that will be half y dot square. So now this is the form of half mv squared. Okay, instead of m, I am choosing that differential mass. Now why am I doing this? Because this is a distributed mass, and I cannot just lump this by a single particle. So I'll just take a small element, and that small element can be approximated by a particle. The mass of that particle is dmr, and I say half dmr times the velocity squared. Okay, so this will give me the small kinetic energy contributed by this element. So this element contributes an energy of dkr. Okay, now if I want to have an expression for the total kinetic energy contributed by the rod, r is for the rod, then I have to integrate this. So I will say half integrate this thing over dmr, and the integral has to be from 0 to the total mass, which is mr. Now here the dummy variable cannot be equal to this limit, so you just use a, maybe you just use a prime. Okay, prime will just allow you to use a dummy variable of integration. So it's better to call this dm prime rather than dm. Okay, now there are two things we can do here. We need to express this dmr in terms of dy. Okay, so the small mass dmr prime will be equal to the density, mass density rho, times the volume. Now what is the volume? Volume is the cross-sectional area A that is fixed for the rod, and the height of that differential element is dy. Yeah? So it's rho A dy. So I can now replace this as half, and dmr is rho A dy. I also need to do something about this y dot. Now if you think about this y dot, we are talking about this point. Okay, and we want to know its velocity y dot. What is the velocity of this point? Can anyone guess? What is the velocity of this point of the rod? Remember, as this concentrated mass moves at velocity x dot downward, it will stretch the rod, but it cannot move this point. So the velocity at this will be 0. Now you have a gradient of velocity. The velocity will vary from 0 to this maximum value x dot. So which means that the velocity will have a value of 0 at this point and a maximum value of x dot at this point. So in between we can assume a formula where the velocity changes with y. Okay, so I can assume that the velocity y dot will be some fraction of the maximum velocity x dot. Which fraction? That fraction will depend on the extent to which you have crossed the rod. The maximum length is L, and you have only covered y. Okay, so y of L times x dot. Okay, that's a nice assumption, y over L. So I can now replace this y dot with y over L, y over L x dot, and this whole thing is squared. Okay, so it will be uh, y over L x dot squared. Now this limit is 0, this limit is still 0 because y is 0 there, but the upper limit here was mr because this differential was for the mass. Now the differential is the length. Okay, so y goes from 0 to L. The maximum value of y is L. So that limit will change from mr to L, yeah, because of this change of variable. So one more thing is that when you write this formula that y dot is a fraction of x dot, this means that y dot only depends on x dot. This dependence on y will not involve time. Okay, so x dot does not depend on y. It does not depend on y, which means that in this integral dy and y, so this x dot can be taken out because x dot moves independently. Okay, this concentrated mass does not depend on how much the rod shrinks. So you can now, in this final expression for kr, I can take half is already out. I can take this x dot square to be out. Rho times a is already, it's a constant. So I'm left in the integrand with the y squared dy. Yeah, y squared dy. So if I now carry out this integration, I'll have half rho a x dot squared, and it's y cubed over 3, and if I put that limit, it will be L cubed over 3 because the lower limit is 0. And I think I forgot one thing, that this L squared in the denominator will also come out. Okay, yeah, this L also had to come out in squared form. So you will have basically L squared. That L squared will cancel out with this L cube. So I'll be left with half rho a L x dot squared. Now it is in the form of half mv squared. This is velocity, remember, of the concentrated mass. So what we have done cleverly is that this y dot, although it was a velocity, but it was a velocity of a small element. It was not a velocity of the whole thing. We expressed that by the velocity of the concentrated mass, and this provides us a justification for interpreting this quantity as the effective mass of the rod. Okay, I'll just write that r as a superscript. So it's the mass of the effective mass of the rod. Okay, that is rho a L divided by 3. Sorry, don't forget the 3 here. Okay, don't forget the 3 here. But we can do something more here. If this 3 was not there, if I just write rho AL. Now what is rho? Density of the material. A times L is the volume of this whole rod. So that means that rho times A times L is the mass of the rod. So I can now, what I can do here is that I can rewrite this formula as half x dot squared, and I simply say mr over 3 because I know this is mr. So what this gives me is that the equivalent mass of the rod is 1/3 of the total mass. Yeah, 1/3 of the total mass. So if I have a recap, what we did so far is that we started with this body which has a concentrated mass, which has a distributed mass. We approximated the distributed mass by an effective mass which is 1/3 of the total mass of the rod, and now we want to represent this whole body by a single spring and a single mass. So that single spring and that single mass, that m will now be mc, because that is mc is not going anywhere, plus mr over 3. This is the recipe of actually representing something by a mass spring system. You first note down all the concentrated masses, you add them, and then you add the transformation. This is a consequence of that integration. Okay. Now the problem is, just like this table before, why did we need this table? Because we don't want that integration every time. So similarly, we don't want to have this and carry out this integration every time. So for our convenience, we will have these tables. Okay. So the nomenclature now will be, if you have concentrated mass in your diagram, you don't see it here because this is the diagram for the equivalent system. You will have distributed mass MD, you will have, and you want the equivalent lump mass ME. Okay. So let's say you want to represent this concentrated mass and the distributed mass combined by a single equivalent mass and a single equivalent spring, so that you have a simple equation. Then depending on the geometry, if the geometry is simple, just like our diagram had, remember in our diagram we had MR here. So in general we will have MD, D for distributed. That can be either in the form of a rod like this, or it can be any spring, yeah, any real spring. MD, spring with a mass. So it's not an ideal spring now. Yeah, that's why he says helical spring. So in both these cases, the distributed mass will be represented by 1/3, just like we showed in the previous example, and we will simply add it to the concentrated mass, and this will give us the total mass. Okay. If we have a simply supported beam, supported vertically, then this will be half of MD rather than 1/3. If we have a cantilever beam, if the beam is on the side, if the mass is actually located at the side and this side is supported horizontally, then the effective mass of the beam will be 0.23 times the total mass, and this will still be added. And if it's a fixed end beam supported at both ends horizontally and the load is in the middle, then the mass of the beam will be represented by 0.38 times the total mass of the beam, and this MC will be added in all the cases. Okay, this MC is not going anywhere. So you are now expected to use this table. You will not be expected to carry out this integration. Okay, this was only to make the concept clear. So you remember, even in the case of springs, ideal springs, we did not expect any integration. So we can have a similar table for the rotational systems. So IC is the concentrated inertia, ID is the distributed inertia, IE is the equivalent lumped inertia. And rather than looking at this, although this equivalent system is correct, but this diagram is wrong. So I'll fix this diagram. Okay. So basically, what he has in mind is this diagram. This heading should move here, and this heading should move here. Okay. So you have a massless spring K and an equivalent lumped inertia, and this is 1/3. Okay. And this is true for both helical and so this formula should also go there. Okay. And for the rod and torsion, you will use the same formula. So you see that the case for rotation is very simple. You just take 1/3. Okay, all the other complicated geometries are not actually included in this table. We can now start with our first example, and that is, let's say we have a 10 kilogram mass, okay, and it is attached to a spring. Now, normally, if this were an ideal spring, you would not see this mass. Okay, that's the advantage. If you see a spring here and you only are given the value k, this is an ideal spring. But if this is accompanied by some mass, this means that this is a real spring with a mass. So according to our nomenclature, this md is the mass of the spring, the distributed mass, and that will be the concentrated mass. So if I now want to translate this example to symbols, this 10 kilogram is my concentrated mass, and this 1.8 kilogram is the distributed mass of the spring. The effective mass, ME, will be MC plus a third of that, because I know for the helical spring, I will use this formula. Yeah, I'll just plug the values. So this will be 10 plus 0.6 kg. So it's 10.6 kilogram. Now I need to estimate K, okay? So rather than any geometry, so that I could have looked in some table, he has provided me with the frequency. So the natural frequency, 20 Hertz of oscillation. Of course, we can convert that to omega n because that is more convenient, 2 pi fn, so which is 2 times 20 is 40 times pi radian per second. And you know that omega n squared is m over k. No, k over m, I think. K over m. So k must be m times omega n squared. You know the value, and this m will be the effective mass, okay? The overall mass. So I know the value of me and I know the value of omega n, and I just plug these values, okay? I plug this value here and this value here, and I'll get my value of k. The next example, you have a motor which is mounted in the middle of fixed end beam. Now you have to go there and see that the fixed end beam, this looks fixed, but the terminology is not fixed. They call it simply supported. So this cannot be the configuration. Fixed end beam is this one, okay? When it is fixed from both sides horizontally. So, and there we know that the factor to use is not 1/3 but 0.38. So it can be modeled as a mass spring system. The motor mass, because motor is the concentrated mass, and it's in the middle. When it's in the middle, you have to use this configuration, okay? This configuration, this one. So MC is 40 kilogram. MC is 40 kilogram. MD is 13 kilogram. And ME, the effective mass or equivalent mass, will be MC plus 0.38 MD. You plug these values and you will have ME equal to something in kilograms, okay? Now when the motor is placed on the beam, so beam पे जब motor नहीं था तो वो equilibrium में था, but when you place that motor on the beam, it causes an additional static deflection 3 millimeter. So your static deflection है delta ST, which is 3 millimeter. You know that normally you can relate the static deflection by k times its value, static deflection, this should give you mass times gravity. But which mass? In this case, because motor is causing that, the beam's own mass is not causing that, so it will be mc only. Okay, so that means that k is simply equal to mc g divided by the static deflection, and you plug the values. So we have the equivalent mass, we calculated that, we have the spring constant, and the natural frequency. Now for the natural frequency omega n, you have k over m square rooted. Now which m? In this case you will have to take the equivalent mass, the overall mass, because the natural frequency is for the whole system. It's not for the concentrated or distributed system. It's for the whole system. Although I'm leaving this question at this point, you are expected to plug all the values with units. Yeah. And finally, if everything goes correct, your final answer should be in radian per second. Okay. Now this is more or less the same question. Yeah, because you have this fixed beam. Yeah. And this is the concentrated, this is the distributed mass, this is the concentrated mass, which simply means that ME will still be equal to MC plus a third of MD. Yeah. An imbalance in the motor's rotating mass will produce a vertical force F. So this can be seen as the input, and that oscillates at the same frequency. Determine the natural frequency of the beam motor system. The rod shown acts like a spring when axially applied, force stretches or compresses the rod. So here you see that the natural frequency is simply equal to k over ME square rooted. Okay. Determine the equivalent mass of the rod. Okay. Of the mass of the rod. Determine the equivalent mass of the rod. So the equivalent mass of the rod will be this term only. Okay. Remember, this ME is used in calculating the natural frequency, because natural frequency is of the overall system. But here, this last question is about the equivalent mass of the rod. Okay. Or maybe I don't know if it's a typing mistake from the previous. I think this must be something from the previous. Okay. I must have, because normally I copy one question to the next. So this looks like a text from the previous question. So the figure, now the next example has, it shows inertia I1. This is the inertia in the middle, rigidly connected to two shafts. So this is connected to this shaft and this shaft. And remember, there's one thing now. Because this support is rigid, this support is fixed, this support is fixed. So this rod will be between the fixed support and the rotating body. So this means that this will be under a twist. Okay. And this rod will also be under a twist. That's why you have to model this rod by a spring, and you have to model this rod by a spring. You do not model this by a spring. Why? कहने को तो ये भी rod है. We did not represent this by a spring simply because it was a rod. We did that because it was under a twist. This thing is not under a twist. Okay. This is simply moving like a rigid body, and you can have a rigid body moving. Twist is when you have an extended body and you move one thing like this and one thing like that. yeah, one end, and there is a twisting effect. There is no twisting effect on I1, okay, but I2, they are under twisting effect, so that's why we have to model them as springs. The torque, the applied torque is T1. So now we need to derive the equation of motion. Equation of motion के लिए आपको जारी बात है, if we model this, I1 is already there, but you know that these are rods, and those rods will be modeled not just by springs, torsional springs, but they will also have inertia associated with them. So we need to go to that table, this table, because we are now in rotation, and we are considering this scenario. Okay, so अगर इसका rod का inertia I है, तो you have to multiply that by 1/3, and then you have to add it to the concentrated inertia. Now in this question, the concentrated inertia is I1. Yeah, तो उस टेबल में जो IC है वो यहाँ पे I1 है, प्लस a third of distributed mass. Distributed mass यहाँ पे क्या है? I2, and this I2 is coming again, so it's actually I2 plus I2. Okay. So now the total effective mass, effective inertia of this overall system is I1 plus a third of I2 plus a third of I2. So that is I1 plus 2/3 of I2. And now I can have a free body diagram. Okay, the free body diagram will tell me that, okay, the applied moment T1 and the restoring moment, the applied moment T1 supports theta, so I can say theta double dot IE, the effective inertia, and T1 is supporting it, and that restoring torque is against it, so that comes with a minus sign, and you have your equation of motion. This was the easy part. Okay. But this KT is this will be the restoring force from one spring, because there are two springs and they both are opposing. Okay, so this will be twice. Okay, it will be twice. You have to subtract that force twice. Now in part B, you are supposed to calculate the natural frequency, and that is the tricky part. So let's clear everything now and follow the question carefully. I1 is a cylinder of 5 inch in diameter. So इसका जो diameter है वो कितना है? 5 inch and 3 inch long. So इसका मतलब है कि इसका length कितना है? 3 inch. So if I call this D and if I call this L, and I also know the material property. I know the value of G, the shear modulus, and I know density. So now I have G at my disposal, I have density, I have length, I have diameter, and I have shape, which is cylindrical. And all this I need to combine to calculate I1. Now I1, you know, first I need to look at the cylinder. If I have a cylindrical shape with given diameter or given radius, okay, and length, and if I know its mass, let me show you one table so that you don't forget what we are doing. Okay, I can show you this table, and this table we don't have the desired shape because this is a slender rod. The diameter is significant here. I mean, this is the case when the diameter is insignificant. But I am showing you another table where you have circular cylinder. I don't go for the conic one. I don't go for the spherical one. This is a cylinder with significant diameter. Okay, so rather than A, you can think of this as half, yeah, half diameter. and length is given. And if you use this formula, the first one, yeah, because this is about the axis of rotation, So I will use this formula, and remember there I use the total mass m. Okay, so I can now get the inspiration for that from that table, and my formula for I1 will be half m1 mass of the central cylinder, and square of the density. Sorry, square of the diameter, d squared. No, square of the radius. So d by 2 squared. Sorry, yeah, d by 2 squared, because radius is d by 2. Now, what is m1? M1 is density times, I'm using the same density because they all have the same material. Okay, they are all made of steel. So rho times volume. What is the volume? Area, which is pi by 4d squared, times length. So now you can see why I noted this L there. So I have the value of L given to me, 3 inch. I have the value of D, which is 5 inch, square of it, then pi by 4, and then multiply it by rho, which is 115.2 slug, and I multiply this by L, and this I will get something in slug. The mass will be in slug. That value in slugs will be substituted here, and then you finally get your I1 here. The same procedure is followed for I2. Okay, I2, because this is also a rod, it will have its own length. उसका length given है यहाँ पे क्या है, वो 6 inch long है, और उसका diameter 2 inch है. तो ये formula आपने उस पे लगाना है, and once you have those quantities, then don't forget to say, okay, that I1 आपको formula मिल गया, I2 उसको भी 3 पे डिवाइड करना है, और दूसरे I2 को भी 3 पे डिवाइड करना है. This will give you IE. So I have the numerical value for IE. Okay. Similarly, for KT, I will have to go to another table. Remember, I have a cylindrical rod with dimensions and density and G everything. So which table will I look for? I have a table for rotational torsional springs. And if you remember, we had this hollow shaft. So चूंकि हमारे पास ये hollow नहीं है, तो D is 0, and I will simply use this formula, pi d to 4th 32L. So the formula for spring will be pi g d to 4th. ये d अब उसका नहीं रहा, अब इसका अपना d है, ठीक है, जो यहाँ पे क्या है 2 inch है, and divided by 32L, और ये L भी इस टाइम पे 6 inch. I'm using the same symbol, but you know what I'm doing. So that will give me the value of KT. Okay, and of course the effective spring constant will be twice KT, क्योंकि ये यहाँ पे दोनों आपको याद होगा मोमेंट इक्वेशन में ये दोनों ऐड हो रहे थे, ठीक है. सो दे यू कैन थिंक ऑफ देम एज बीइंग इन पैरेलल में आप उसको ऐड करते हैं. सो जब आपको ये सारी चीजें पता चल जाएगी, एंड इफ यू वांट टू नो द नेचुरल फ्रीक्वेंसी, तो नेचुरल फ्रीक्वेंसी का फार्मूला क्या है, स्क्वायर रूटेड k ओवर i, क्योंकि ये रोटेशनल प्रॉब्लम है और ये kt है, तो kt आपके पास 2kt हो जाएगा, या क्योंकि दो स्प्रिंग्स है, और I आपके पास हो जाएगा IE. Okay, and then you plug the values, and if everything is right, your answer should be in radian per second. Okay, now this is the next problem, and read this carefully, and this should remind you of some other example. Okay, you have the vibration of a motor mounted on a beam. Remember, if I ignore this cantilever thing, and if I just replace this with fixed support, just to remind you that we have done something like that. It can be modeled by a mass spring system. The motor weighs, motor का weight given है, mass की जगह weight given है, beam का weight given है, ठीक है. And you can actually, if you want, you can convert them to masses. You simply divide it by g. That's not a big deal. When the motor is placed on the beam, it causes an additional static deflection. Remember, this is something we have done. Find the equivalent mass and the equivalent spring. So if I go back, if I take you back to this, it's exactly the same problem. Example 4.3.8. देखो ये fixed end support है, motor mounted in the middle है, ठीक है. नो ये नहीं है, सॉरी ये नहीं है, ये वाला नहीं है, ये वाला है, ठीक है. मोटर माउंटेड इन द मिडल, फिक्स्ड इन बीम, मोटर मास गिवन है 40 किलोग्राम, वहां पे 40 किलोग्राम की जगह क्या गिवन है, वेट गिवन है WC, एंड यू नो हाउ टू कन्वर्ट WC टू MC. बीम का मास गिवन है, सो MD गिवन है, और हमारे उस प्रॉब्लम में WD गिवन है. यू कैन कन्वर्ट दैट टू MD. When the motor is placed on the beam, it causes additional static deflection. ये भी उसमें given है. And find the equivalent mass, the spring constant, and the natural frequency. तो अब इसमें इसका मतलब है कि इस क्वेश्चन में और वो जो प्रॉब्लम है उसमें फर्क सिर्फ किस चीज का है, ये वैल्यूज तो पता है, वैल्यूज का फर्क तो मैं उसको वैसे ही नहीं मानता. तो जो बुनियादी फर्क है वो ये है कि फिक्स्ड एंड बीम हैज बीन रिप्लेस्ड विद कैंटिलीवर बीम. द रेस्ट इज जस्ट चेंज ऑफ वैल्यूज. तो हम क्या करेंगे कि हमने बेसिकली एक लाइन चेंज करनी है. ओके, इसका जो मास है, इफेक्टिव मास, हमने लास्ट टाइम ये किया था 0.38. दिस 0.38 was for fixed beam. Okay, now you replace this with cantilever beam, so you just replace that 0.38 with 0.23. Okay, so this 0.38 will be replaced with 0.23, and the rest is just calculation with different values. Okay. वन थिंग कि आपको पता है कि ये 40 पाउंड्स और ये 9 पाउंड को आपने डिवाइड कर देना है 32 पाउंड पर पाउंड फीट पर नहीं सॉरी 32 feet per second squared, 32 feet per second squared, and this will give you actually mass, the mass and slugs. वो आपको जारी बात है यूनिट्स के साथ डील करना पड़ेगा. if I just carry that out, just let's say मेरे पास WC है 40 पाउंड, ठीक है, 40 पाउंड. so you see, because you need equivalent mass M, so उसके लिए you first need to convert this into MC, and that MC is WC over G. W is 40 pound and G is 32 feet per second squared. Okay, so this will give you 40 divided by 32, and feet divided by pound divided by feet per second square should give you slug, because you are dealing with US customary system. Okay, यहाँ पे कोई किलो मिली माइक्रो नहीं है, तो ये it should give you that, and same goes for MD. Okay, that will also be in slug, and then you plug everything in this formula and you have your ME. ठीक है. और स्प्रिंग कांस्टेंट आपको पता है कि स्प्रिंग कांस्टेंट के लिए आपको टेबल देखना पड़ेगा. टेबल कौन सा देखना पड़ेगा आपको? बेसिकली हमने इस प्रॉब्लम में स्प्रिंग कांस्टेंट भी देखना था, और स्प्रिंग कांस्टेंट आपके पास कौन सा बीम है? फिक्स्ड एंड बीम. ओके, अब फिक्स्ड एंड बीम में मुझे देखना है कि फिक्स्ड एंड बीम के लिए स्प्रिंग कांस्टेंट कहां से आएगा. यस, फिक्स्ड एंड बीम के लिए ये तो हमने डिस्कस ही नहीं किया. लेट मी जस्ट, फिक्स्ड एंड बीम के लिए ये टेबल आपको देखना पड़ेगा, ठीक है। तो इसमें कौन सा वो है, देखो ना, ये नहीं है कि ये तो ओपन रॉड है, यो है, ये सिंपली सपोर्टेड है, ये कैंटिलीवर है। वी हैव टू गो फॉर फिक्स्ड इन बीम एंड दैट एग्जांपल, और उसके लिए फार्मूला ये है 16 टाइम्स E टाइम्स W टाइम्स H क्यूब ओवर L क्यूब। जो प्रॉब्लम लास्ट में हम डिस्कस कर रहे थे उसमें क्या होगा, उसमें you will use this formula for the K। तो दोनों में चूंकि K रिक्वायर्ड है, दोनों प्रॉब्लम में K रिक्वायर्ड है, तो K की वैल्यू आपको वहां से मिलेगी। तो इसका मतलब इस प्रॉब्लम में आपने दो टेबल्स यूज करने हैं, ठीक है, टू टेबल्स, one table for the effective inertia or effective mass to be precise, and one table for the effective um, stiffness। दो दो टेबल आपको यहाँ पे यूज करने पड़ेंगे। नेचुरल फ्रीक्वेंसी आपको टेबल नहीं चाहिए, उसके लिए तो आपको सिर्फ ये फार्मूला चाहिए के ओवर एन, ठीक है।
एक्सक्यूज मी सर।
यस,
तो यहाँ पे वो फॉर्मूला भी तो यूज हो सकता है, एम के डेल्टा, एम जी इज इक्वल टू के डेल्टा।
वो यहाँ पे हम यूज कर सकते हैं।
सर इट कॉजेज एन एडिशनल स्टैटिक डिफ्लेक्शन की बात हो
नहीं
रही
नहीं,
है।
वो तो अच्छा, आप ये कह रहे हैं कि हम वो यूज कर सकते हैं।
यस सर, सर के फाइंड करने के
अच्छा
लिए।
अच्छा अच्छा, ठीक है ठीक है ठीक है, बिल्कुल बिल्कुल बिल्कुल, वो असल में वो मैंने मिस किया ना, मे बी दैट इज व्हाई वी नेवर नीडेड दैट टेबल। ये आप कहना चाहते हैं ना?
यस सर।
ठीक है, सही है, ठीक है। ये असल में मैं जब जब इस एग्जांपल को, प्रॉब्लम को मैप कर रहा था, तो मैं ये भूल गया था कि हमारे पास तो ये भी था। ठीक है, मैं भी ये दिस वाज गिवन जस्ट टू 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 अवॉइड दैट टेबल। लेकिन ये डिस्कस करना इसलिए जरूरी है कि हर क्वेश्चन में तो ये नहीं दिया गिवन होगा, स्टूडेंट शुड बी अवेयर, दैट वाज अ गुड थिंग।
यस सर।
ओके, सो डू यू गाइस हैव एनी क्वेश्चंस? ये सारे टेबल्स जितने भी है ना, और फार्मूला शीट, दिस विल बी प्रोवाइडेड टू यू इन एग्जाम। सो ये इसलिए मैं आपको बता रहा हूँ कि आप ऐसा ना हो, आपने कभी ना देखा हो वहां पे, आप टेबल फार्मूला शीट अगर यूज करना भी आपको नहीं आता, तो दैट विल बी वेरी अनफॉर्चुनेट। ओके, so you should at least, whenever you solve these problems at home, you should be using these tables so that you are comfortable with that. Stop recording.